Hi, I will be talking about quantum versus randomized communication complexity with efficient players. This is based on a joint work with Ranras and Avishay Tal. The setting is communication complexity. There is a function that takes as input two binary string and outputs a bit. This function may be partial, which means that it is defined on a subset of points, or it may be total, which means that it is defined on all points. There are two parties, Alice and Bob. Alice gets one of the inputs and Bob gets the other input. Their goal is to compute this function. To do so, they need to exchange messages with each other, and their goal is to minimize the amount of communication, that is, the number of bits that they exchange. One simple protocol is to have Alice send her entire input to Bob, or Bob send his entire input to Alice. This costs m or n bits of communication. So by a small cost protocol, we mean a protocol that does much better than this. That is, its cost is polylogarithmic in m and n. This is the general setting of communication complexity. Let us see a few different models of communication. In the classical randomized setting, Alice and Bob share public random coins, which they can toss arbitrarily many times, and their goal is to compute f of xy with probability at least 2/3 while minimizing the worst case amount of communication. In the quantum setting, there are two differences. The first is that Alice and Bob share EPR pairs. The second is that they can exchange qubits. This is an inherently probabilistic model, and as before, their goal is to compute f of xy with probability at least 2/3 while minimizing the number of qubits that they exchange. We will also be interested in the number of rounds of a communication protocol. In two-way communication, Alice and Bob can interact with each other. In one-way communication, Alice sends a message to Bob, and Bob must decide whether the function is 0 or 1. In simultaneous communication, Alice and Bob do not talk to each other. Instead, there is a third party, a referee, Charlie, to whom both Alice and Bob send messages. Charlie, upon receiving the messages from Alice and Bob, needs to declare whether the function is 0 or 1. Sometimes we allow Alice and Bob to share EPR pairs, sometimes we don't. It depends on the model. These are successively weaker models of communication. That is, there are functions that are easy in the two-way model, but hard in the one-way model. Similarly, there are functions that are easy in the one-way model, but hard in the simultaneous model. Now that I've introduced the relevant communication models, let us state the main problem of interest. Is there a communication problem that has a small cost quantum protocol, but no small cost classical protocol? Is there a function that is easy to communicate when you can exchange qubits, but hard when you can only exchange classical bits? So does quantum provide advantage in the world of communication complexity? For total functions, we don't know the answer. It could very well be that every quantum protocol for a total function can be converted into a classical protocol with minimal overhead. This is a major open question. For partial functions, on the other hand, there is a long line of research spanning over 20 years, all of which demonstrates that quantum communication can provide more power. That is, quantum communication can provide exponential advantages over classical communication for partial functions. The first such result was established by Boorman, Cleve, and Wigderson, who showed that in the zero-error setting, when we want to answer correctly with probability 1, there are partial functions that are easy in the quantum simultaneous model, but exponentially harder in the classical two-way model. This suggests that a rather weak model of quantum communication can exponentially outperform a rather powerful classical model of communication. In the bounded error setting, when we want to answer correctly with probability at least 2/3, the first such result was shown by Ranras. He showed that quantum two-way can exponentially outperform randomized two-way. A similar result was shown for quantum one-way versus randomized one-way. This was strengthened to a separation between quantum one-way and randomized two-way. Finally, the state-of-the-art separation is between quantum simultaneous, where Alice and Bob share entanglement, and randomized two-way. Let us take a closer look at this result. The state-of-the-art result is due to Gawinski. He shows that there is a partial function which has a small cost quantum simultaneous protocol when Alice and Bob share a few EPR pairs. However, there is no randomized protocol of small cost regardless of the number of rounds. This result essentially subsumes most of the prior separations on bounded error quantum versus bounded error classical. Secondly, it demonstrates that a rather weak model of quantum communication can exponentially outperform a rather powerful model of classical communication. One drawback of this result, in the context of our work, is that the quantum protocol is not efficient. We say that a quantum protocol is efficient if it can be implemented by a quantum circuit of small size with oracle access to the inputs. This means two things. The first is that the amount of post-processing and pre-processing done by the players is not too much in comparison to the size of the messages that they send. That is, everything that Alice, Bob, and Charlie do can be implemented by quantum circuits of polylogarithmic size. Secondly, the oracle access to the inputs just means that Alice and Bob don't need to read their input bit by bit. They can make a few queries to their input in superposition and still be able to execute the protocol. In Gawinski's result, the quantum protocol is not efficient because the referee has to do n many measurements one after the other. Our result addresses this aspect. We show that there is a partial function which has an efficient small cost quantum simultaneous protocol when Alice and Bob share a few EPR pairs. However, there is no randomized protocol of small cost regardless of the number of rounds. Our parameters are slightly weaker than Gawinski's result, but the important difference is that the quantum protocol in our result is efficient. This means that everything that Alice, Bob, and Charlie do can be implemented by circuits of small size with oracle access to the input. In other words, we qualitatively recover Gawinski's separation between quantum simultaneous and randomized two-way. Furthermore, our separation has the property that the quantum protocol is efficient. That is, the actions of all players can be implemented by circuits of small size with oracle access to the inputs. What did we know about efficient separations? To the best of our knowledge, this has not been explicitly addressed in the setting of quantum versus classical separation. In most of the previous separations, the quantum parties seem to be inefficient. And they're inefficient in many different ways. One is that the referee has to do a lot of post-processing. This is the case in Gawinski's result. Another reason is the players need to make multiple probes into their input. This is the case for most of the other separations that I mentioned. Nevertheless, we did have an efficient separation prior to this work. This was between quantum two-way and randomized two-way. This is obtained by taking the existent efficient separations in the query complexity world and lifting them to communication complexity using the query to communication lifting theorems. The reason this only gives us an efficient separation between two-way quantum and two-way randomized is that the gadgets used in these lifting theorems seem to introduce two new rounds into the communication protocol. Our result unites these two lines of work. We recover the state-of-the-art result using quantum protocols where all the parties are efficient. Secondly, we provide a new lower bound technique for randomized communication complexity based on Fourier analytic techniques from these two works. The first is the polarizing random walks result of Chattopadhyay et al. The second is the oracle separation result of BQP and PH. Now that I've introduced our results, let me demonstrate the function for which our separation holds. Our function is based on the Hadamard matrix. So let capital N be 2 to the little n. The Hadamard matrix of size capital N by capital N is defined as follows. Each row and column can be indexed by a bit string of length little n. Let A and B be bit strings of length little n. The A, Bth entry is plus or minus 1 over square root capital N. The sign is plus if the inner product between the row and the column is 0 mod 2, and the sign is minus if the inner product between the row and column is 1 mod 2. Here is an example of a 2 by 2 Hadamard matrix. The Hadamard matrix is a unitary matrix. It has close connections with the Fourier transform. So for instance, if you take the truth table of a function and apply the Hadamard matrix, what you get is the truth table of the Fourier transform of the function up to some normalization factor. We're now ready to define the correlation of a vector. The correlation of a vector is essentially the inner product between the second half of the vector and the Hadamard transform of the first half, up to some normalization. In other words, it measures the correlation between the second half of the vector and the Fourier transform of the first half, up to normalization. The correlation function was first introduced by Aronson, who showed that estimating the correlation of a vector is easy when you have quantum query access to the entries of the vector, but is difficult when you only have classical query access. The correlation function has thus already been used to separate quantum and classical in the query complexity world. We show a separation in the communication complexity world. For convenience, our inputs are now from -1, 1 instead of 0, 1, and we use the pointwise product instead of XOR. Our problem is as follows, the correlation communication problem. Alice gets X, Bob gets Y. Their goal is to find out if X XOR Y has high correlation or whether it has low correlation, where this high and low differ by roughly 1 over log n, where n is roughly the input size. If you're familiar with the lifting literature, this is a lift of the correlation query problem with XOR as the gadget. Our main separation is for this function. That is, we show that this function has an efficient quantum simultaneous protocol of small cost when Alice and Bob share a few EPR pairs. However, this function has no randomized protocol of small cost, regardless of the number of rounds. This is our main theorem. In the next 10 minutes or so, I will describe a proof of this main theorem. The quantum upper bound essentially follows from existing work. We will instead focus on the proof of the randomized lower bound. By the Yavos min-max principle, it suffices to produce two distributions, one on the yes instances of the correlation problem and one on the no instances, such that no deterministic protocols of small cost can distinguish them with considerable advantage. We now demonstrate our hard distributions. To do so, we make use of the correlation distribution as defined in the oracle separation result of Raz and Tal. It's not too important what this distribution is for the rest of the talk, but to have a picture in mind, the distribution is as follows. In the first step, we sample a random Gaussian vector where each entry has mean 0 and variance epsilon. Furthermore, the second half is exactly the Hadamard transform of the first half. This vector is in some sense as correlated as can be. In the second step, we perform a randomized rounding of z to get a Boolean vector. The first thing that Raz and Tal show is that a vector sampled from this distribution has high correlation on expectation. For now, let us imagine that this holds with high probability. We now define our hard distributions for the communication problem. For the no instances, a string z is sampled uniformly at random, whereas for the yes instances, z is sampled from the correlation distribution. Now, in both cases, a string x is sampled uniformly at random. Alice gets x, Bob gets x XOR z. Note that the distribution of no instances is the following distribution. Alice and Bob get two uniformly random strings that are independent of each other. The distribution of yes instances is as follows. Alice and Bob get two uniformly random strings conditioned on their XOR being drawn from the correlation distribution. Note that when two strings are sampled uniformly at random, independently, their XOR is also uniformly random strings, and it has low correlation with high probability, intuitively speaking, but this can be formalized. On the other hand, for the distribution on yes instances, the XOR is distributed according to the correlation distribution, which I just mentioned has high correlation. So these are valid hard distributions. And our main theorem is that deterministic protocols of small cost cannot distinguish these two distributions with considerable advantage. That is, for all deterministic protocols of cost at most c, their advantage in distinguishing these two distributions is at most c square over square root n. In other words, when the cost is less than n to the 1/4, the advantage in distinguishing these two distributions is really small. In the next few minutes, I will describe an overview of the proof of this theorem. So our goal is to show that for deterministic protocols of cost at most c, their advantage in distinguishing these two distributions is at most c square over square root n. Every protocol of cost c can be broken up into 2 to the c many rectangles. This is a standard argument in communication complexity. So it suffices to show that rectangles that are not too small cannot distinguish these two distributions. That is, we want to show that for sets A and B, whose measure is roughly 2 to the minus c, the advantage of the rectangle indicator A times indicator B in distinguishing these two distributions is at most this quantity, which is c square over square root n times 1 over 2 to the c. If we could prove this, then by adding up this inequality over all rectangles in the partition, we will get our desired inequality. So now our goal is to show this inequality. We introduce an important simplification here, which is the convolution of functions. The convolution of indicator A and indicator B is denoted by indicator A star indicator B. It's defined exactly as shown in this equation. Note that this quantity appears in both of these terms. So we can substitute this back and rewrite our goal as follows. So now our goal is to show that the function indicator A star indicator B has similar expectations under the uniform distribution and under the correlation distribution. How do we go about showing this? We make use of existing results. It follows from the works of Chattopadhyay et al. And Raz and Tal that if you want to show that a certain function can't distinguish between the uniform distribution and the correlation distribution, it suffices to prove a level 2 Fourier bound on this function. To be more precise, we need a nice family of Boolean functions. This nice is some technical condition which is closed under restrictions. This is satisfied by most of the functions that you could think of that are built out of small cost protocols, small cost decision trees, and so on. But let's just ignore this condition for now. This theorem says if that for all functions in your family, the level 2 Fourier mass is at most alpha, then the advantage that this function family has in distinguishing the uniform distribution from the correlation distribution is at most alpha over square root n. That is, if any nice family of Boolean functions has small level 2 Fourier mass, it cannot distinguish between the uniform distribution and a distribution built out of weakly correlated Gaussians. We make use of this result as follows. So our goal was to show that indicator A star indicator B cannot distinguish between the uniform distribution and a distribution built out of weakly correlated Gaussians. We reduce this to showing a bound on the level 2 Fourier mass of indicator A star indicator B. So now our goal is to just prove this Fourier bound. How do we prove this Fourier bound? The first observation is that the Fourier coefficients of the convolution are the product of Fourier coefficients. Using this, we can simplify the expression for the level 2 mass as follows. We now apply Cauchy-Schwarz to obtain this. We now bound each of these terms in this inequality as follows. We use the level k inequalities. This appears as an application of hypercontractivity in Ryan O'Donnell's book. This allows us to bound the sum of squares of level 2 Fourier coefficients of an indicator function of a subset in terms of the measure of that subset. This inequality and its variants have been used in most of the previous separations on quantum versus classical communication complexity, so it is not surprising that it shows up in our work as well. Substituting this inequality in our previous inequality, we get exactly what we want. This concludes the proof of the level 2 Fourier bound. To summarize what we did, we considered this function f of z, which is obtained by taking a convolution of low-cost communication protocols. We bounded the level 2 Fourier mass of that function, and we use existing works to conclude that this function cannot distinguish between the uniform distribution and the correlation distribution with considerable advantage. And these two facts together gave us the lower bound on the communication complexity. Let me conclude by mentioning some open questions. The first is that Can we improve the lower bound to omega square root n? We believe that this is the correct lower bound for the function that we defined earlier. To prove this, it would suffice to prove a level 2 Fourier bound of order C on this function f of z. The other direction is to prove separations between other models of communication complexity. For example, we could weaken the model of quantum, for example, quantum simultaneous without entanglement. Or we could prove advantages against stronger classical models. This concludes my talk. Thank you for watching.